So this is the title of my talk. I am from Trento. I'm also a member of the INFN. Actually, I realized while I was waiting that I didn't put the ENAF logo, but in principle, I'm also associated with ENAF through Padova. So sorry for that. Don't tell to your colleagues. Well, I'd say it's a different association, but I'm really glad that I'm now also member of ENAF as an associate. I'm also, some of the work that I'm going to show you has been also founded by EPRIN, so I'm supposed to show this slide because of that. But okay, let's start with the scientific part of my talk. I will try in the first part to give, unfortunately brief, but I hope large enough overview about what is a binary neutron star merger, at least from my personal perspective as a modelist. Can you see my pointer?
Yes.
Okay,
yes.
In case I won, okay. Okay, so let's start first to say what is a binary neutron star merger, which are the most relevant features that enter this kind of process. So a binary neutron star mergers happens when in the universe we have a binary system formed by two neutron stars which are gravitationally bounded. At the leading order, we can think about this system being described by the masses of the two neutron stars, let's say M1 and M2 in this cartoon. And of course, the structure of the neutron star is ruled by the equation of state of nuclear matter, which sets, for example, the radius and the antenna structure. These are the most important parameters. Due to the emission of gravitational wave, this in spiral phase is characterized by a shrinking of the orbit because gravitational waves carry away angular momentum and energy in such a way that on a time scale, which is typically of the order of a few gigayears, a system which is located at astronomical distances can actually shrink up to the point where the two neutron stars cannot do much than just to touch and to coalesce. So this is the so-called merger phase. Despite the fact that this cosmic dance can last 1 gigayear or several gigayears, the final phases are extremely fast because this is the dynamical timescale of a binary system at merger. And the merger phase happens when practically the two stars touches each other. And here the typical dynamical timescale is of the order of 1 millisecond. After this phase, let's say the fate of a merger depends very much on the masses of the two neutron stars and on the equation of state. So in this cartoon, you can see that there is a path, which I will go briefly through here on the top. But at any stage, you can see that actually there is an arrow that points to a black hole. This is because at any stage from the merger on, it is possible that gravity eventually wins and form a black hole. This is not obvious, depends on the masses and on the equation of state. If the system is more massive or the equation of state is particularly soft, this can happen more easily, let's say, while if the masses are relatively light or the equation of state is very stiff, it's possible that the system will collapse to a black hole only at late time or even never, even if the formation of a stable neutron star is seen as a corner case. Anyway, after the merger itself, there is a phase which lasts 10, 20 milliseconds, where the two neutron stars are still fusing, so the two cores are forming a kind of a cigar shape, which is still a very strong gravitational wave emitter. So the emission of gravitational wave is still the dominant process in this phase here, because of this shape. However, due to the fact that the kinetic energy of the merging binary is converted into, at least a part of that, into internal energy, the temperature increases. If you want just to get a feeling of what is the speed at the two neutron stars collide, you can make just back of the envelope calculation, and it turns out that the orbital speed at merger is 40% of the speed of light. So as I said, during this collision, the kinetic energy, a fraction of it gets converted into kinetic energy, and so the system becomes hot. This is very peculiar because a neutron star can be typically described as a totally degenerate system with zero temperature, while the temperature that are reached a few milliseconds after the merger are of the order of 10 or 50 or even 100 MeV. And so the system starts to produce copious amount of neutrinos because this is the kind of radiation that escapes first. The photons are completely trapped, and the system starts to produce neutrino with a typical luminosity of the order of 10 to the 53 erg per second, which is comparable to the luminosity of core collapse supernovae. The subsequent phase in which there is the formation of a central object, which becomes more and more spherical, surrounded by a disk where the matter that has been spread out settles inside this disk is called the viscous phase because in addition to the cooling through neutrinos, there are MHD processes which are that produce some viscosity that actually drive a accretion disk viscosity process. And only at later time, the remnant is either a black hole surrounded by a disk or just an isolated, very massive neutron star that can actually collapse due to the spin down. This is more or less what happens to most of the matter. So when I spoke before about the figure here about the disk, I was speaking about probably 99% of the mass which formed the two original neutron stars. However, there is a few percent of the total mass of the system which, through several different mechanisms, can become unbound. So that is really expelled from the system, so gravitationally becomes gravitationally unbound and goes and reach the interstellar medium. Of course, this is a very minority, just maybe 1 or 2% of the mass of the system. However, this is the most interesting part of the story for the rest of the universe, because this is matter that will actually pollute the rest of the universe. Since this is matter coming from a neutron star, you can easily understand that this matter is very peculiar. In particular, it's extremely rich in neutron, and this is measured by a quantity that we call the electron fraction. You can see here the definition. The electron fraction is defined as the net fraction of electrons, so electrons minus positron, over the baryon density. And if you think about charge neutrality, you can easily understand that the electron fraction is a measure of the relative amount of neutron and proton in the system because of charge neutrality. And as you can see, having an electron fraction of 0.5 means that the number of protons and the number of neutrons are equal, while having a YE, an electron fraction, which is much smaller than 1, means that the system is much more enriched in neutrons rather than in protons. So, as I said, few percent of matter gets expelled, and with time, we are getting more and more confident about the mechanism that can expel this matter. The first one, because it was the first one that happens in a merger, but it was also the first one that was studied already 20 years ago, is the so-called dynamical ejecta. This is the kind of process that happens in the first 5 milliseconds before merger, and you can see in this cartoon what's going on. Here this is actually a result from a simulation. You can see the two neutron stars that start to touch, but before they get touched, they actually get deformed by the tidal interaction among the two. And there is a part of the neutron star, the one that is actually here, far apart from the center, that gets ballistically ejected because of the interaction of the two, or the collision of the two stars. This is the so-called tidal ejecta. At the same time, in the center, you can imagine how violent could be the merger, because you have two objects that have more or less 1.5 solar masses that crash against each other. So inside here, deep inside the merger, there is matter that gets squeezed by the interaction between the two neutron stars. And because of the squeezing and of the compression, this matter gets heated up. And the only thing that this matter can do is to expand because of thermal pressure. And actually, this matter launches some shocks that actually unbound some matter. The kind of matter that is ejected over this small amount of time is very fast. It travels at 20–30% of the speed of light, but it's also a very thin amount of matter. So it's something that, depending on the equation of state and on the masses, is between 10 to the minus 4 and 10 to the minus 2 solar masses, but 10 to the minus 2 is very extreme. So as a just a number to keep in mind, dynamical ejecta is 10 to the minus 3. For many, many years, this has been the only way in which we thought matter could be expelled. However, recent simulations show that the disk, if you remember, I told you that after a merger, there is the formation of a compact object in the center surrounded by a disk. And I told you that this disk is a viscous disk in which neutrinos also act. Longer simulation has shown that on timescale much longer, which are comparable to the cooling timescale of the system and with the viscous timescale of the system, neutrinos and viscosity of magnetic origin can actually unbind a significant fraction of matter, which is roughly 10 to 40% of the mass of the disk, at a speed which is lower than the previous one, but still significant, 10% of the speed of light. And now, if you consider that the simulation show that the disk can have the masses between 10 to the minus 2 and 10 to the minus 1, the amount of mass that can be expelled in the form of this wind actually overcomes significantly the one of the dynamical ejecta. So it could be of the order of 10 to the minus 2 or even 10 to the minus 1. So most of the matter we think that could come from this wind. Recently, we have also started to perform other set of simulation that showed another kind of ejecta, which is actually, I would say, a special case of the so-called disk winds, but have a very different physical origin. We call it spiral wave winds ejecta. They happen more or less on a similar time scale, maybe a bit earlier. And the reason is the following. Imagine that in the center, the system does not collapse to a black hole. You form these massive remnants that tends to become more and more spherical because of gravitational wave emission. However, the system, this object, is unstable through the formation of some M1 deformation, so some hydrodynamical instability that prevent it to become a perfect sphere. And this M1 spiral mode, you can imagine it as a spoon. Imagine that you have a cup of milk and then you put in the center a spoon and you start to mix, okay? The result is that the spoon provides some angular momentum that it's transmitted in the outer part of the fluid. Here, it happens the same. You can see from this simulation here, the red spot is nothing but the flux of angular momentum. This angular momentum is transferred from the central object outwards, and when it reaches the edges of the disk, matter starts to become unbound. This new mechanism has been proven to be very efficient in terms of ejection rate, something like 10% of the solar masses per second. The typical property are intermediate between the dynamical and the disk wind ejecta. The only caveat is that this is a mechanism that requires the formation of a massive neutron star in the center. As soon as the central object collapses to a black hole, this mechanism clearly shuts off, and we are left with a more canonical disk wind. So just keep in mind, there are these different kind of ejecta, and in particular, the spiral wave wind is very efficient, but it requires the presence of a central object in the center. What happens to this matter which is expelled and expanded into the interstellar medium? As I said, this matter is very peculiar because it's very rich in neutron, and since the 70s, when this kind of binary were first discovered, it was clear that this kind of matter could be the site where the so-called R-process nucleosynthesis takes form. R-process nucleosynthesis is one of the two main processes responsible for the formation of heavy elements. We know that the key reaction is the capture of a neutron by an already formed heavy nucleus, and this is the way in which nature can produce most, if not all, the nuclei heavier than iron. And in the case that the density of neutron is so high that the time scale for the neutron capture is much smaller than the time scale for the beta decay, this is exactly what happens in the case of the R-process nucleosynthesis, where R stands for rapid because of this reason. And in particular, the density that we measure inside the ejecta of a binary neutron star merger is perfect to match the condition typically for the R-process nucleosynthesis. So R-process nucleosynthesis is a very complicated task, is out of equilibrium reaction. One would need a nuclear reaction to model it carefully. Luckily for us, if the entropy is low, and the entropy typically in this ejecta tends to be relatively low, there is one dominant parameter which at the leading order, if you don't care too much about the details, determine the outcome of the nucleosynthesis, and it's the Y, the electron fraction. So in some sense, as you can see from this plot that I think was actually made for me by Diego a few years ago, if you set in a tracer element the electron fraction of the particle, more or less irrespectively of the other parameters like entropy and expansion timescale, you get the different element production pattern. You can see here the total final abundance of a fluid element with the different electron fraction as a function of the mass number. The dots are represent the solar pattern, and you can see that the electron fraction influence heavily the kind of production that you have, but in a way which is not very continuous. What do I mean? What do I mean is that if the electron fraction is, let's say, larger than 0.25, we can actually produce elements between the so-called first and second R process peak. By the way, sorry, this is not the solar R process, it's the residual. So it's what we think come from the R process. As you can see, if the YE is relatively high, so 0.25, we can actually produce elements just above the iron group elements down to the so-called second R process peak. If you want to go beyond that level, you need to set the initial neutron abundance high enough, which means that you need an electron fraction of below 0.25. And if you really want, and this is crucial, for example, to produce lanthanide, if you wanted to really produce the heaviest element, including uranium and thorium, here the actinides, then you need an initial neutron abundance extreme of the order of 1 to 10. So in some sense, as I said, the YE influences at the leading order the kind of element that we produce because it influences the initial production. You can understand that the ratio between neutrons and protons become crucial in order to understand what is the nucleosynthesis. So the question is, if you have a matter, nuclear matter, what does influence the ratio between neutrons and protons? It's weak reaction, because as I told you, the bi-neutron star merger, the matter gets heated such that it produces neutrinos. Neutrinos can be emitted and absorbed. And so these two reactions, in particular the electron capture and the positron capture of a proton or a neutron, and of course the inverse of neutrino absorption decay, becomes crucial in order to establish what is the precise value of the YE. And the precise value of YE determines what is later the abundance. So it's a very complicated path that we have to go if you want to predict abundances. In particular, neutrino, this is actually my main topic. So this is the cartoon that you have to have in mind. So this is the central hot massive neutron star in the center. This is the accretion disk. You have neutrino production from all the region deep inside the remnant and inside the disk. And the idea is that the neutrino, of course, they stream away because they have a small cross-section. However, they have a non-negligible probability to be captured by matter in their way out. And so the properties of the matter that is expelled later depends crucially on the fact that the neutrino had the chance to interact through this reaction, for example, to change the way. Indeed, if you perform a simulation without neutrino absorption or with neutrino absorption, the property of the ejecta changes dramatically. So in this plot, what you can see is a function of the polar angle. So theta equals 0 means matter expelled in the equator. Theta equal, sorry, the other way around. Theta equals 0, it's matter expelled toward the pole, while theta equal 90 is matter expelled toward the equator, and color-coded the amount of matter that is expelled at that particular latitude. Here on the y-axis, you can see what is the electron fraction of the matter that is expelled at that specific angle. As you can see, if you don't include the possibility for neutrino to be reabsorbed by this reaction, so if you artificially switch off this reaction, the typical YE of the ejecta at all angles is practically below 0.25. And if you remember, if matter is below 0.25, there is the robust production of lanthanide and actinides, but no production of the light element, as you can see from here. However, once you introduce neutrino absorption, along the pole where neutrino have an easier way to escape from the system, there is this reaction at work, and so the matter that was seated here gets irradiated by neutrino, they get absorbed, the neutrons get converted into proton, and the electron fraction rises. Now the picture is very interesting because you have that matter at low latitude here can produce the very heavy element, while matter at higher latitude produces the lightest one. So this was very crucial to understand that in a binary neutron star merger, all this trajectory can be found once you take into account the effect of neutrino. This was not clear 20 years ago, where people thought that neutrino were not relevant, and so we could produce only the heavy part of their process element. And indeed, as you can see, the nucleosynthesis pattern changed dramatically. If you don't include the neutrino reaction, you produce all the heaviest part of the residual R process, solar residual R process element from the second to the third peak, but you underproduce the first peak. Once you introduce the effect of neutrino, the Y distribution moves also at larger values, and this larger value actually allows to better match the solar pattern also in the low mass number region. This is all very important. Say, binary neutron star merger are important not only for nucleosynthesis, but also from an astrophysical perspective, also because they produce counterparts. Of course, one of the most famous are the gamma ray burst, because you have the central black hole surrounded by a magnetized accretion disk, and for example, through Blamford-Sanae mechanism, you can actually launch a relativistic jet which produces a gamma ray burst. This is what we think is the mechanism behind gamma ray burst, at least short gamma ray burst production. At the same time, there is another kind of transient which is very peculiar related to this, and it's called kilonova transient. And this is exactly the proof, the smoking gun, that our process nucleosynthesis is at work, because when this ejecta gets expelled into the interstellar medium, it undergoes our process nucleosynthesis, that's okay, but the nuclei that are produced are radioactively unstable. And so while matter is expanding during the first hours or days, there is a constant nuclear heating due to the decay of the elements which are produced. And as soon as the matter has expanded enough to become optically transparent, there is a quasi-thermal emission, at least in the first days, which is actually due to the energy deposit in the ejecta by the nuclear heating. This, up to a few years ago, this was all theoretical, if you want, but of course, with GW170817, we had a spectacular confirmation of that, because in GW170817, there was the gravitational signal of a binary neutron star merger, followed by a short gamma ray burst, roughly 1.7 second after, and there was the kilonova signal that we have studied intensively over the last, after, let's say, starting from 11 hours after the merger up to a couple of weeks after we have signal from it. Okay, so I hope I convince you that binary neutron star merger are astrophysical key player, because they are primary source of gravitational waves, source of our process element, and we had a confirmation because of the kilonova emission, which is exactly powered by their process element. They are central engines of gamma ray burst. Of course, the challenge here is how can we study them at the quantitative level? How can we relate our understanding with what we observe? And here the problem is that it's a multi-physics process, because it's general relativity involved, but the equation of state is governed by the nuclear reaction. I told you that neutrinos are fundamental because they change the abundances and they regulate the evolution of the disk. And of course, also magnetic field, MHD effect are relevant. So practically all the four interactions are relevant. But in addition to that, it's a multi-scale process, because the merger happens in a box, if you want, of roughly 100 kilometers, because this is the radius of the neutron star and this is the side of the disk. And it happens on a very short time scale. But if you think about the counterpart, the short gamma ray burst and the kilonova happens on much longer time scale, ranging from seconds to days, and on a much larger time scale, because the disk has to expand, as well as the kilonova to become transparent. But all the different interaction and all the scale are intimately related, because what enters here in the strong field dynamics determine later what appears and what is emitted by the counterpart. So the challenge here is to model this, and this is actually the greatest part of my job, in terms of merger simulation. So the small scale and strong field dynamics, we do this through numerical relativity code, so simulation in full GR, using the best input physics that we can, finite temperature, composition-dependent equation of state, and neutrino radiation, and this is of course very challenging and still work in progress. And in terms of counterparts, I'm not an expert on gamma ray burst. I'm a bit more involved with the kilonova, and here state-of-the-art is radiative transfer simulation. I do not do radiative transfer simulation. I tend to rely more on simplified models that allows us to, for example, making parameter estimate. But here there is a lot of relevant input physics that range from atomic physics to nuclear physics, and of course, has this root in the outcome of simulation. So this is very, very challenging. This more or less concluded the kind of introduction that I had for you. Now I want to show you some explicit cases in which I show you how we can interpret the outcome of a simulation the outcome of an observation based on what we have simulated. I would start with the GW170817 and the work that actually I did with Diego and also with Sergio. So as you probably know, GW170817 had an associated kilonova, 2017 GFO, and this is characterized by a bright ultraviolet component that has its peak around 1 day, that is typically called in papers the blue component, that was followed by another component, which is typically called the red one, that were brighter in the infrared with a peak at 5 days. So there was a lot of effort also from our group in order to explain this feature, but in parallel to that, there was also the study of a bit more detailed information about the spectrum. To study the spectrum of a kilonova came out to be a much more challenging task that people probably thought in the beginning. The first element that was claimed to be observed, funny enough, was not an R process element, was strontium, that we think mostly come from S process, also from R process, but it was not europium or gold that are typically R process element. However, there have been a couple of papers that claim that there was a clear identification of a strontium feature, and they also provide an estimate of the amount of mass that was produced as strontium in this ejecta. Here reported the number, so it's a few times 10 to the minus 5, more or less. Actually, it was noticed, I think, by Enrico Cappellaro when we started this work, that the strontium line that is associated to this emission is actually very good overlap with an helium-2 line. And so at that time, we asked ourselves two questions. Do we expect strontium in the ejecta of a binary neutron star merger? Because as I said, it's not europium, it's not gold, it's not uranium and thorium, it's a light element, and it's not a R process only element. If yes, how much, and does it say something about the event? And the second question that we ask ourselves, is it possible that what we observe is not helium, is not strontium, but helium? So in order to do that, we have considered some simulation. We had actually a catalog with more than 80 simulations that are reported in these two papers, but we decided to take a subset of this simulation, so two distinct binaries with two different mass ratio. The mass ratio is the ratio between the masses, so we have a symmetric, very symmetric merger in which the masses of the two neutron stars were identical, and one where one is practically double the other. We took a numerical relativity code, whiskey THC. We put a state-of-the-art equation of state, at least in the field, final temperature, composition dependent. We included neutrino, this is crucial. And we had also some viscosity, and we tested things at different resolution because it's a numerical process. What we did mostly with the Diego was we studied the nucleosynthesis that came out from this merger. So we studied the properties of the ejecta. We post-process the run with the data taken from Skynet, and we extract the pattern of the abundances. And this picture, I think, can reflect nicely what we were observing. So the first thing to remark is that all the models that we analyzed produce a dynamical ejecta, as expected, and some of them produce long-lived remnant, and also they produce a spiral wave wind. So with the collaborators of that paper, we decided to study separately the different contributions, the one from the dynamical ejecta and the one from the wind. And in particular, we focus on the very light element, hydrogen and helium, because this is what we want to investigate, and on strontium, for example. And as you can see, the production, the fact that we did produce some strontium was not surprising at all. We do have a pretty robust production of strontium in all the models, with only the exception of a very unequal merger where we do expect strontium not to be present because there the physics is very different. The production of neutrino is very much suppressed. There is the formation of a black hole, and so we do expect here not to have strontium. So unless, as long as you produce a massive neutron star remnant, the production of strontium is actually very much predicted, together with the production of helium. So this first calculation was not able to distinguish among the two. As you can see, helium has more spread, but still it's present in the dynamical ejecta, which is very much what we expect. Then somehow we just went and make a quantitative statement. And so what we have seen is that the amount of strontium which is produced in the first ejecta, which means the dynamical ejecta, is actually already a significant fraction, 3 times 10 to the minus 5. So in other words, it would be sufficient to explain what we have observed. But then, what does this say about the strontium? Well, in principle, if you know that strontium is produced both in the dynamical ejecta and in the spiral wave wind, and what you have in the dynamical ejecta is already enough to explain what you observed, the conclusion to that is that the spiral wave wind could have lasted only a small amount of time. Otherwise, we would have observed much more strontium. So assuming a strontium mass of the order of 5 times 10 to the minus 5, which is the upper limit that we got from observation, the time scale over which the wind could have lasted actually reduces to few milliseconds. So what does this mean? This means that our result suggests that the GW170817 produces a remnant that collapses to a black hole relatively quickly. Otherwise, we would have seen much more strontium, because strontium is a relatively easy element to form whenever you have a massive neutron star in the center, which can irradiate with neutrinos and produce strontium, because strontium can be produced in a robust way when the electron fraction gets high enough, so when neutrino had the time to interact. What about helium? So I want to skip here the part about hydrogen. What about helium? We have observed also helium here, and in particular, we have identified with Diego for the first time a new chain to produce helium through deuterium and tritium. We have used, especially I think Achille Fiore used TARDIS in order to see if we could see feature which were if it was possible to see the spectral feature of helium, and as soon as only LTE conditions were established, the helium was practically not possible to be seen. And even at a later time, when we had a new version of TARDIS with some non-LTE effect, it turned out that the amount of helium that our simulation was producing was not enough to explain the feature that we have observed. So in some sense, the result of our paper is that it is very likely that the feature that we observe is from strontium, in the sense that with simulation we can explain that amount of strontium. The helium is present, but maybe not enough, unless there are non-LT effects which we're not able to take into account. I want just to let you notice that say a few years after, 2 years after our paper, there was a paper from a Japanese group that claimed that they were able to explain the same feature with helium. So they say that our intuition about the possible ambiguity was actually, let's say, plausible. And if they make the calculation with full non-LTE transfer, they are able. I checked yesterday, and the paper is still an archive. It has not been published yet. But I think it's very interesting alternative. Okay, so this is the first application that we did. Sorry, how much time do I have left? 10 minutes?
Yeah, you have 10 minutes, about 10.
Okay. Then I have a second. So this is the first example of how modeling in details the merger outcome and comparing it with detailed observation can actually shed a light on the properties. I want to present now a second paper that actually came out just a few months ago on the archive, and just been recently accepted from a PhD student of mine. And in this paper, we ask the title, we ask a provocative question. Well, not so provocative. Did the kilonova set off in our neighborhood 3 million years ago? And why did we ask our question? Because in some sense, what we can do in order to understand our process nucleosynthesis, for example, to observe the solar abundance pattern and try to understand the nuclear physics that produce that. The problem with the solar abundance pattern is that this comes from many different events. So probably many different supernovae, maybe merger, have contributed to that. And this, of course, makes very dirty as an example, because it comes from the superposition of many things. Astronomers and astrophysicists are always searching for much cleaner environment in which only one event could have polluted what we observe. And for example, this is typically metal-poor star, where we think that what we observe is just the result of one event. Another possible scenario is the observation of Arp-Rosen's abundance patterns, which are traceable to single events because they are characterized by live radioactive isotopes. So we know that more or less there are of the order of 10 elements which have a decay lifetime of the order of 10 or 100 mega years. And so the idea would be to observe an object, or even on Earth, the abundances of these elements so that we can trace back their origin to events that happen in the nearby future. And because they are going anyway to decay, then we have hope to, how can I say, to identify just by the measuring the ratio between, for example, two of these elements, the place where they've been produced. For example, there was this very interesting result that came out in 2021, where people were analyzing deep sea crust samples on Earth, so in the ocean. I don't remember which ocean, but they went and analyzed the deep sea crust, and they were able, for the first time, to identify plutonium-244. There was also iron 60. Actually, the iron 60 detection is actually much older than that, something like 6 or 7 years older. And you can see, for example, here in this graph, as a function of the age of the sediment, the fact that the iron 60 has two clear peaks. A first peak around 3.5 million years ago, and the second one weaker. And this was, as I said, rather old result, not old, but let's say 2015, 2016 was already detected. The news in 2021 is that in the same sediment, they were actually able to isolate a few, let's say, around 180 plutonium-24 element atom, and they could actually compute the ratio among the two, and the ratio is of the order of 53 10 to the minus 6. And of course, the question is, how can we interpret these two recent peaks? Well, let's forget for one moment the second. The second is it's much harder to understand with a single case. But let's try we want to interpret the detection of the peak in the iron at the same time as the peak in plutonium. Why this is very challenging? Because iron is usually synthesized in core collapse supernovae. There is practically all the papers that I found in the literature about iron 60 in deep sea sediment said, well, this is a clear product of a core collapse supernovae. What makes the puzzle is that the plutonium, on the other hand, is a strong R-process element, which is typically synthesized, we have seen, in binary neutron star merger, and so it's something that powers the kilonova. Typically, standard core collapse supernovae are not able to synthesize plutonium, and so people started to, assuming the existence of special classes of core collapse supernovae. This is actually much older than the problem of the plutonium in the deep sediment. Special classes of core collapse supernovae can solve many problems, but they are very speculative. We don't know if there are, if they exist. It's still very speculative. And so the people started to say, well, is it really possible to explain at the same time the iron and the plutonium, assuming a single source? And so there are a lot of papers where, no, not a lot, but few papers that they explore both the single source, so the possibility to have plutonium and iron synthesized in the same site, or multiple sources. So the plutonium was synthesized first by a BNS merger, then this polluted the environment, and then came a supernova ejecta, and this make a drag of the ejecta. And so when they arrive on the Earth, there is the iron from the recent supernova and the plutonium that was there because it was produced before. These are the two main ideas. We had a look at a few papers where the people tried to explain with single scenario, kilonova, and we were very surprised that the kilonova was always unable to explain the plutonium over iron. And so we went to dig a bit into the hypothesis, and we have seen that these 2 points that seems to rule out by order of magnitude the kilonova were actually making pretty strong assumptions. In particular, they always consider a merger that was forming a binary black hole, so there was no long-lived remnant. And moreover, they were taking the ejecta, and they were forgetting that this ejecta is emitted at different angle with different properties. They were just isotopizing everything as the mixing was perfect. So what we did, okay, this is more detailed. So what we did, we have considered other simulation from our database of GW170817, different from the previous one. We have seen distinct binary, the same setup as before, so I don't go through again. But the important point is that all the simulation that we did consider didn't form a black hole. So they had a long-lived remnant, and so they had also a spiral wave wind ejecta. Then we have computed the ratio, but not summing over all integral, but as a function of the angle and the polar angle of the emission, and this is what came out. So you see here, unfortunately, it's not the plutonium over iron, but it's iron over plutonium, but it's the same. And the red here is the result of the observation. And as you can see, there are two models that without any fine-tuning, just these are data from the simulation, without any fine-tuning, they are actually able to explain in a relatively large angle interval, so between 20 and 60, they are actually able to observe what we have seen. So in some sense, the idea is that if you consider the fact that the kilonova emission is highly anisotropic and the nucleosynthesis depend on the interaction of the neutrino, there is a region of the space of the solid angle in which you can produce more iron, less plutonium, in a way that the ratio matches the observation. We have also computed the distance at which this kilonova would have happened, this merger would have happened, and these are actually the two models that you can see here. We just inverted this equation here with respect to the distance, the radioactivity distance, and it was very nice to see that both the plutonium and the iron would actually more or less be at the same level as the distance, so the line here represented the local bubble. So the bubble in which the solar system is embedded, and that we think is the one in which the supernova can actually enrich the Earth. So in some sense, it's a possible nearby event that happened at the same distance as we would expect the supernova to happen that has already shaped the recent past, in the recent past, the abundances. How much, we also tested how much is this process dependent on the time, and as you can see, we don't need to fine-tune the time. The time is actually possible within 1 mega year. So in some sense, it's a relatively robust result.
Albino, you have 5 minutes.
Okay, I'm done. This is my last slide. Sorry, I have much more material, but that's normal for me. This is my last slide. So our point here is not that for sure there was a nearby kilonova. The point of this paper is that you cannot rule out so easily binary neutron star merger. Clearly, special classes of supernova can do the job, but the main message of this paper is that if you take into account the complexity of a binary neutron star merger and what happens in interaction, the fact that you can have a long-lived remnant, it's still on the table the fact that it could have been a kilonova. We also indicate, actually it's not our idea, it's an idea taken from another paper, that we can actually have more live isotopes that can actually break the degeneracy. And in this paper, in the letter, we have already computed the rate that we expect. So if in the future we will be able to measure one of these elements, we could have another point to add to our graph to understand if things are going on. To be fair, I must say that there is already one other point, which is a rather peculiar element, which is manganese 53, which is even more challenging because it's typically related with tape 1A supernovae. And in our simulation, it's almost absent. And so in some sense, we could say that, oh, this is already a disproof. However, we checked which are the conditions that are relevant to produce manganese 53, and it's a YE of the order of 0.45, 0.5, which is not observed in our simulation at the moment. However, we do have a new simulation with a more detailed neutrino transport, and in this simulation, we can clearly see that there is a bunch of ejecta that gets so high YE. So I'm really excited by redoing the analysis with the new simulation, because there are hope that with the new simulation, with more detailed neutrino transport, we will be actually able to see some manganese, and then of course there we can compute also the ratio for that. There was a second part that I knew already that I didn't have time, so I just go to my conclusion. So I hope I convince you that binary neutron star merger are sites that are very exciting, also for theoretical physicists or theoretical astrophysicists like myself, because matter here reaches the most extreme gravity, density, and temperature condition. And if you want to give interpretation to the observation, it's fundamental to also make the modeling and the correct modeling. The numerical modeling of binary neutron star merger has dramatically improved, but there is still a lot of work to do. All the neutrino transport, the MHD mechanism, the microphysics, these are all to do. There are all to do items on our list. However, if you do the proper job, there is a large number of information that can be extracted. And of course, we have to combine them with the electromagnetic counterparts, because this is very complementary to gravitational wave signal. But we have to combine only the combination of detailed merger and counterpart models are actually, I think it's the way to go. It's the most promising way to do that. And this can only be, so the possibility, the usage of sophisticated model of binary neutron merger is really the key to exploit this wonderful laboratory. I think I can stop here, and I'm ready to take questions.
Okay, thank you. Thanks, Albino. And we have time for questions. Please unmute yourself if you're from remote, or here, if there's somebody that has questions, you can come to this workstation and we can talk.
Hi, Albino, very nice talk. And it's really interesting what you found with this last paper. I guess that many times speaking with people, they say, okay, but no, neutron star mergers just do lanthanides or actinides. And because they don't realize that the nucleosynthesis is rich starting from also the light elements. Like, for instance, strontium coming from a neutron star merger, it's impossible. Well, it's impossible because you never computed the model. And I guess that the more models are available in the next years, and more, let's say, the observers will be guided to understanding.
No, I totally agree. Let's say, I do fear something in all that, and it's that with core collapse it was similar. People thought that core collapse can do everything, but then when they started to put the neutrinos, it turned out that they're not able to make the area. So now I fear that also with BNS merger we will do that. I think that the variety of condition here should save us. I'm not saying that strontium is the most important one, or that we have a lot of iron from this, but they are partially produced. Maybe they are not relevant at the level of galactic chemical evolution,
for sure,
because the rate kills you. And here there are a lot of hypotheses. For example, you have to make the hypothesis that the system does not collapse to a black hole, and this is already a subset of cases. But when you look at one star, when you look at one observation, all these statistical things don't play anymore, because what you observe is what you observed. Maybe it's a corner case, but it's what you observed. And so, no, I agree with you. I'm still a bit afraid. I don't want that our neutrinos screw up too many things. But I see in a positive way that there is a huge variety of conditions that can come out from that. It's not as simple as some people think.
And then I have a question, which is not directly related to your presentation, but what's your personal feeling, your guess, of next neutron star or neutron star black hole detection?
Oh, well, I'm not, I don't know. The more, you know, we started with GW170817 and we thought that life was easy because, you know, we switched on Virgo and a few days after we had a beautiful BNS merger with the kilonova short gamma rebirth. And then we thought, okay, now we switch on Virgo and LIGO again together. We wait 1 year, we are going to get incredible things. And of course, it didn't happen. And now if you talk to, you know, people that computes rates, yeah, they told you, yeah, GW170817 will happen once every 10 years.
Okay.
So, but let's say, I think the future, more or less, I mean, if IT goes, it gets funded and we can really build such a kind of detector, I mean, I saw that there is Eleonora in the audience, we can ask her, we are going to have many of those events. So maybe now we are still in a phase where it's exceptional, but with more and more, you know, our horizon and our sensitivity will be large, this should become a routine. I hope that next spring we will have a BNS merger with the counterpart, but this depends very much on Virgo.
Okay. Let's cross the fingers.
Yeah.
Thank you.
Thanks, Sergio. Other questions? Prego, Diego, unmute yourself.
Yes. So thank you, Albino, for the nice presentation. I have a question about your last table, the one containing all the unstable isotopes. So there is another astrophysical scenario in which you have all these stable isotopes that is the early solar system. So my question is, what about if a kilonova set off 4.6 billion years ago, close to the solar system?
But let's say, I think that most of this would be actually disappeared, right?
Yeah, that's the point. But I mean, for example, you see in the early solar system that iodine is present. All these isotopes that you have listed are present. So some of them could be produced through a neutron star merger.
Yeah, I mean, yes. Well, I think the what makes the difference is the ratio. Now I don't have here the plot, but I think in the paper from what is it? This Wang et al. They actually make the plot of all these elements as a function of time, and then you can see how, you know, because they have different decay time, then they have the curves bend at very different times. And so I think the challenge here is to match exactly the ratio that you observe. This is what actually can pinpoint the time of the I don't know if this answers your question or if I didn't.
Yeah. I mean, in my opinion, it could be interesting in looking at this problem, because probably you can say something about the last event that contaminated the solar system, if a BNS was the cause, let's say.
Because you would expect a deviation from some of these elements or in other sediments that are not.
You have information in the meteorites for these elements or these isotopes.
Okay. So you say if I just go in a kind of detection that I know that has not been polluted afterwards, I can actually disentangle the two.
Yeah.
So what you are saying is that one could repeat this exercise, but not on the sediment, but on the meteorite.
Yes, because for the meteorites, you have all this list of isotopes, so you can see if you can match some of them and infer something on the properties of the BNS merger.
Okay. I see. I understand. Okay, that's interesting. I didn't know that we had all of those.
Yeah, for example, I remember that there was a paper that claimed that curium and iodine came from the same air process event, for example.
Okay.
Also because they have a very similar lifetime.
Okay. Oh, interesting. I didn't check.
Okay.
Other questions? Albino, I have one. Is probably very naive, and you said, I mean, you showed that your simulations have quite a bunch of ingredients, like the equation of state, and then the way the neutrino is treated. And I suppose there is also some kind. You mentioned probably also magnetic fields. I mean, what is the state of the art for? And what is the most challenging ingredient, and what do we need more now? To refine those kind of ingredients to concentrate something. What would be your guess? Or
No. That's a very good question. Of course, it depends a bit on the bias of you, because there was a comment in one slide that I didn't comment much, but I think it's very important. Simulation often contains subset of necessary physics. The point is that it's up to us to say what is this subset. And of course, if you publish a paper, you typically in the introduction, you claim that what you didn't put is not relevant in that scenario, but you didn't put it and prove it. You don't put and you use it as an argument. So in this sense, we are biased. I must say that when I started my PhD, there were simulation in full GR that had no neutrinos, that use the polytropic equation of state, and they have a resolution that now we consider too coarse to make any quantitative statement. Now we are less than 20 years after, and we do have much larger, much smaller resolution, so much better resolution. We have finite temperature equation of state. We have transport, which is now distant, I would say, with M1. We are working, so we have MHD, several MHD code on the market. The challenge now, in my opinion, is to improve the rate, because the neutrino rates that we use are very, very approximated. And the microphysics is also not always adequate, in my opinion. So there is a lot of work to do. And the other thing is to combine everything together. You can find a lot of simulation with detailed neutrino transport. You can find a lot of simulation with the magnetic fields, but combine the two is highly non-trivial, because there are a lot of acts that the code must do in the different regimes, and to combine the two acts, we have just started. So the combination of magnetic field and neutrino is still not so robust, as well as the level of the microphysics. This is what we need at the moment, in my opinion.
Okay, thanks. If there are no other questions, let's again thank Albino, and
thank you.
It was a pleasure to have you here again. And we have another webinar in 2 weeks with Claudia Pulsoni from the Max Planck Institute for Astrophysics. And good afternoon, everybody. Ciao Albino, grazie.
Ciao, grazie a voi.
Ciao Albino.